Hello, this is a brief um, presentation on teaching general physics labs in a remote environment at USF. And so what we would like to do is first introduce the strategies that we implement. Now, a lot of these strategies are what we would normally do in the face-to-face environment, but it's just how they're being done in the remote environment that's key here. We introduce the basic physical concepts, assess the level of comprehension, identify experimental variables and error. And this is a very noteworthy strategy. Promote creative student design and testing. Since they can't have access to our labs at USF, that doesn't mean they can't do experiments. And analyze the results with Excel and form a conclusion. So introducing the basic physical concepts, the method of delivery, our publisher was able to digitize our manual, and so in the manual there's a lot of experiments that go over a lot of the theoretical background so that the student has some idea the kind of physics that they're going to be exploring in these experiments. We have pre-lab video instruction outlining theory and other details. This is provided extra for them because, again, these are individual researchers. They don't have lab groups. They work by themselves, and it's not synchronous. Using Canvas pages for instructions and methodologies. This is another key step here because the instructions in the manual when it comes to collecting data have to be changed a bit, modified to whatever they're going to be doing at home. Providing as many visuals as possible is essential for student learning. So assessing student learning outcomes, what we like to do is give them pre-lab quizzes through Canvas. They get 2 attempts. We like for them to see which ones they missed and then go research why they missed the question. And student predictions is also essential. Trying to make sense of the physical world and the concepts and equations and theories that we put forth to them. We want them to see if they can imagine. So an example here, we're looking at coffee filters, and we would like for them to predict, based on how many coffee filters, there was like 2, 4, 6, 8 coffee filters, what the velocity versus time curves might look like based on everything they've learned so far. And also they have some exercises to do at home to kind of gear them up for this. Like, for example, dropping a piece of paper that is just unfolded or crunched up versus one that they ball up, and they drop those two and just notice the way they fall and give them an idea of what those curves might look like. This is actual data from doing this particular lab, but the idea was for them to show a pattern of what would happen if we keep adding coffee filters and dropping them. To digress a bit, I'd like to talk about how the 2020 strategy would look like. We'd like to develop more synchronous methods. That would take a lot of planning and something that we think could be achieved in August. And so we're proposing the hybrid method, where we only have a small handful of students in the lab at a time and the others work at home online. That's going to be obviously a challenge for our TAs, but we think that we can, with the summer development that we've done, we could pull that off a little bit easier. So proposing 3 student groups where they meet online with each other, and they meet online with the TA. This is more or less of a quality approach than a quantity. We have to minimize the number of experiments we do, but we'll maximize the learning for each one. And so making connections is a very important part of assessing their level of comprehension. Here's a coupled math system, and one of the things they were to do is simply, make diagrams. A force diagram is typically done in a mechanics lab, and here that's all the forces that they would believe to encounter for the smart car, which you see as red. Friction, it just stopped, if I could add a little bit of physics here. The friction that you see there, that little small arrow pointing down the incline, again, that's a connection that they should have made in the previous lab. That friction was so small, and you would like for them to retain those and not just separate, go from lab and then something completely independent next week, but try to make connections from previous weeks. And so, we give them opportunities to ask questions. What is doing work on that car? And how would we vary that amount of work from those identifiable forces that are doing the work? So these are things that we engage them with, and we want to make sure that essentially they stay on top of their learning. In a nutshell, we're introducing at this level the qualitative analysis. And we hope that up to this point that we've done a solid job in helping the students with this type of analysis. Going into that phase now where they're looking at the experiment and studying the design, identifying variables is very important in the lab. Which ones are dependent, independent, and controlled. Our face-to-face meetings, we're able to walk around the room and probe them, ask them questions about the design. But it's hard and challenging to do that remotely. But we do ask the questions, and we get them to study various pictures, videos, and try to think of, what are the variables in the experiment? What are we actually, based on what our objectives are, what are these controlled or dependent or independent variables, and how, how the design could be improved or whatnot. Of course, in any physics lab there is error, and so identifying this error is just as important as the variables. What is your error in reading a meter? What are systematic errors? Is there anything that appears to be shifted or miscalibrated? These are things that mostly are done in the lab, but we can still focus on a lot of random errors, as you can see from this experiment of Coulomb's law. Reading those positions, how many digits are they good to, and just what is their error in reading those positions, plus or minus some value. And then again, questions to ponder: are we even using the correct theoretical framework, for a particular experiment? I mean, is there any modifications that we need to think about? Best precision. How can we achieve the best precision? And they have to think about that at home, especially if they're doing measurements. Finding a measuring device that gives them to the millimeter, having magnifying glasses to, again, try to minimize that error. How many significant digits, therefore, would they be using and reporting a certain final value? So minimization of error is something that they can definitely think about at home. In fact, it would probably come up more often than not. We want the student, essentially, we want the student to study that design. Study the design that's presented in our general physics labs or any simulation such as the one you see here. So we provide as many demonstrations as possible. Filming our work in the general physics labs at USF is a big part of this. And why is that we now are transitioning into what we call quantitative analysis. So promote creative student design and testing. Here, you have just a simple pendulum, and it's investigating the binomial expansion. This is something that a student just designed at home to do some measurements of period. And so, again, we provide clues and hints as to how the design could work and how error was minimized. And it's up to the student to think about it based on all of the strategies that they've seen up to this point. And, in some cases, projectile motion and other things could be achieved if, the design is suitable. Ice and aluminum foil have there's almost zero friction. And so they're able to do some nice pure theoretical calculations and do measurements and test their design in that way. And even in the General Physics 2 environment, we do have some things for them to do. PowerPoint is amazing. If you just provide enough instruction for them, examples. For example, this student took the circuit that you see there, and with the rules that govern the uses of that breadboard, they're able to just click and drag and size resistors, wires, and make up connections, connecting up that circuit as they would do in a normal lab. So you can make the circuit a little bit more complex, and they could still pull it off. So these are nice little ways in which we get the students to think abstractly and be a part of an experiment. What would they have read on that meter ideally, and so forth. The TA obviously is the meter. They would measure what the current is, and it should match up to what they report here. Of course, using Excel as a tool is a must. This is a spreadsheet. We try to promote, especially in a remote environment, put a lot of emphasis on structure, organization, completeness, neatness. And so the students in their environment at home, they put a lot of time in presentation, and any employer would expect to see a nice clear presentation and a summary, which they all provide in Excel. So just a summary of remote teaching, we provide as much background in the theory, assess their level of knowledge, identify variables, error, measurement, precision, possible independent designs. We want them to do as much work in this particular area, especially a lot of our students will like to work as graduate students in a real lab. Good habits and good recognition, good lab presence is a must. And use available tools for analysis, presentation, and summary. Thank you for your attention.